Right now, the multi-billion-dollar chip powering the exact device you're listening on is, well, mathematically speaking, the result of a highly educated guess.
Yeah, which is kind of wild to think about.
It really is. I mean, we like to think of our microchips as these perfectly engineered miniature cities, right? Where every single transistor is placed with just absolute precision.
Right.
But the truth is, at that microscopic level, perfection is simply too computationally expensive to calculate. So the software that's designing your hardware is playing this massive optimization game that involves, huge compromises, or at least it was.
Exactly, it was.
Welcome to the deep dive. Our mission today is to take a highly technical stack of sources, bypass all that dense jargon, and really extract the real aha moments just for you.
And we have a really great one today.
We do. Today we're looking at a fascinating 2026 presentation and paper. It's by an author known as Luck036, and it's titled Exhaustive Circuit Partitioning via Middle Levels Gray Code.
It's quite a title.
Oh, yeah. So, okay, let's unpack this, because we were going to look at how a 40-year-old, purely abstract mathematical mystery was finally solved, and then just ingeniously hot-wired into the software that physically optimizes the microchips we use every single day.
It really is this remarkable collision of pure theoretical math and like gritty computer engineering.
Yeah.
If you look at the background behind me, you can actually visualize the two worlds colliding. We have these intricate layered hypergraph diagrams representing the modern engineering side, right? And they're layered right over this chalk-dusted blackboard filled with combinatorial math from the 1980s.
Which is such a cool image.
Yeah, that overlap is exactly where today's breakthrough happens. But to really understand the solution, I think we first need to establish the baseline of the problem.
Let's do that. So the industry term here is EDA, which stands for Electronic Design Automation.
Right.
It's essentially the software that builds the hardware. And the massive bottleneck in ED that we are really focusing on today is called circuit partitioning. I want to ground this for you, the listener. Just imagine a microchip not as a flat piece of silicon, but as a sprawling, complex network of logic gates and memory blocks and controllers. How do we even represent that mathematically?
Well, we use something called a hypergraph. So a standard graph, the kind most people learn about in school, just has dots connected by lines.
Right, point A to point B.
Exactly. One line connects exactly two dots. But in a hypergraph, those lines, which we actually call nets, they act more like lassos.
Lassos.
Yeah. So a single net can wrap around and connect 3, 4, or even like 50 different modules all at the exact same time.
Okay, wow. And the goal of circuit partitioning is to take this massive hypergraph lassoing millions of modules and split it up. You want to divide these modules into a specific number of parts, say 2 parts, partition A and partition B.
Right.
But you are fighting 2 massive constraints here. First, obviously, physical space. You have to keep the partitions strictly balanced. You can't just cram 99% of your logic gates into partition A and leave 1% in B.
Right. The physical space definitely has to be managed. But the second constraint is the truly punishing one, honestly. It's about minimizing the cut cost.
Cut cost.
Yeah. So every time one of those hypergraph lassos, a net, spans across the boundary between partition A and partition B, it has to be physically wired across the chip.
Oh, I see.
And that severed connection creates signal latency, it consumes excess power, and it generates heat. So your core objective is to slice the circuit in a way that cuts the absolute minimum number of nets.
Which sounds totally simple until you hit the mathematical wall. Because circuit partitioning is an NP-hard problem.
Oh, absolutely.
And for anyone who needs a quick refresher, NP-hard essentially means that as the number of modules on your chip grows, the number of possible ways to split them just explodes exponentially.
It scales incredibly fast.
Yeah, so finding the absolute perfect, mathematically guaranteed best split becomes literally impossible. You could put the world's fastest supercomputer on it, and you'd be calculating until the heat death of the universe.
Because of that NP-hard reality, the industry doesn't even attempt to find perfection. They rely on heuristics.
Shortcuts.
Exactly. Shortcuts that provide a good enough answer in a reasonable amount of time. And the reigning champion of these shortcuts, the absolute industry standard, is the Fiducia-Matthesi's algorithm, usually just called FM.
FM, right. I really want to break down how this FM algorithm works because it really highlights the flaw we're trying to fix today.
Go for it.
So FM operates by moving exactly one module at a time across the boundary line. It scans every single module and calculates a gain. It basically asks, if I move this specific module from partition A to partition B, how many nets do I remove from the cut minus how many nets do I accidentally drag into the cut.
Right, a simple cost benefit check.
Exactly. It calculates that math for every module, picks the single move with the highest positive gain, and makes the jump. Then it just recalculates and does it again.
The mechanism is entirely greedy. It doesn't look 2 steps ahead or 3 steps ahead. It only looks for the immediate best step available right in front of it.
I always picture the FM algorithm like a hiker trying to find the absolute lowest valley in a sprawling mountain range, but they're caught in a ridiculously thick fog.
Oh, that's a great analogy.
Yeah, they just cannot see the big picture.
Yeah.
So they just feel the ground with their boots. If it slopes down, they take a step. They keep walking downhill one step at a time, picking the steepest downward slope available.
And eventually they hit the bottom.
Right. The ground levels out.
Yeah.
And every direction they step goes back uphill. The hiker stops and says, "Great, I'm at the bottom." But they only found the bottom of a valley. They are completely trapped in a local minima. They might have missed a massive sprawling canyon just on the other side of the ridge.
If we connect this to the bigger picture, the FM algorithm trapping us in local minima means the quality of the final circuit design is heavily dependent on where that hiker started walking.
Wow. Right.
The initial, often totally random setup dictates the final result.
That is incredibly frustrating. Like if the software designing our chips is basically taking a greedy guess based on a random starting point, we're leaving massive amounts of performance and efficiency on the table.
We really are.
So we need a way to find that absolute lowest valley, the global optimum, without having to guess where to drop our hiker. But to make it play nicely with our existing EDA software, we need a method that still moves exactly one module at a time.
And that requirement, moving one module at a time while exhaustively checking everything, is what brings us to the middle level's gray code.
Okay, here we go.
To grasp how this solves the EDA dilemma, we need to pull a concept from pure combinatorics, specifically the middle level's graph.
Right.
Imagine a massive multidimensional shape called a hypercube. The middle level's graph is a specific slice straight through the center of that hypercube.
Let me try to ground that for you listening, because hypercubes get abstract fast. Let's talk in bit strings, strings of ones and zeros. The points on this middle level's graph are all the possible bit strings of a certain length. The rule is that the length of the string is an odd number, which the math calls 2n plus 1.
Right.
And the number of ones in that string has to be almost perfectly balanced with the zeros exactly n or n plus 1 ones.
Let's walk through an example. Let's say n is 2. That makes our string length 5 bits long.
Okay, 5 bits.
According to the rule, every valid bit string in our graph must have exactly 2 ones, or exactly 3 ones. So a string like 11000 is a valid point.
Got it. And the connections between these points.
An edge only exists between 2-bit strings if they differ by exactly 1 flipped bit. So from your string of 1100, if we flip the middle 0 to a 1, we get 111000.
Ah, okay.
We went from a string with 2 ones to a string with 3 ones. That is a valid move along the graph.
And when we apply this back to our microchips, it maps perfectly. We have a list of modules. A 0 means a module sits in partition A. A 1 means it sits in partition B. Because the bit string is always balanced, always containing exactly 2 or 3 ones in our 5-bit example, it perfectly represents a balanced two-way partition of our circuit.
So in 1982, mathematicians proposed a problem around this specific graph. Could you find a Hamiltonian cycle? Could you draw a path that visits every single valid bit string exactly once and returns to the start by only ever flipping 1 bit at a time?
It sounds like a fun brain teaser, but it remained an open, unsolved mystery in combinatorics for nearly 40 years.
It really did. Nobody could prove it.
Right. It wasn't until 2014 that a mathematician named Muses proved it was theoretically possible. And it took until 2019 for Gregor, Muetz, and Neumann Paulo to provide a complete constructive proof. They actually built the algorithm to map the path.
And the algorithm they built is remarkably elegant. It is memoryless. It doesn't need a massive database to remember where it's been.
Oh, really?
Yeah, it calculates the very next step based entirely on the current vertex, using a complex recursive tree structure, a dict path, to map out the flip sequences on the fly.
Here's where it gets really interesting. Look at the mechanical synergy. This mathematical gray code flips exactly 1 bit at a time to check every single valid, balanced bit string.
Right.
That is the exact same mechanical operation as our greedy FM algorithm. FM moves 1 module at a time. Gray code flips 1 bit at a time. But instead of being a blind hiker walking downhill until they get stuck, the gray code is an exhaustive mathematical map of the entire mountain range.
What's fascinating here is how it entirely changes the guarantee we can offer the engineer. With the FM algorithm, you're guaranteed a local optimum, a good enough valley.
Right.
But with the middle levels gray code, because it exhaustively checks every single valid state in the graph, you are guaranteed the global optimum. You find the absolute deepest canyon, period.
Okay. I'm going to play the skeptic for a second here.
Go ahead.
We just established earlier that circuit partitioning is an NP-hard problem. If we are exhaustively checking every single combination of a modern microchip, which has millions of transistors, won't that exponential explosion of states take forever? Even with a mathematically perfect map, you still have to actually walk the path.
You're totally right. The math is entirely unforgiving on that front. The scaling of states visited follows this combinatorial formula, 2 times the combination of 2n plus 1 choose n.
Yeah.
The explosion is violent.
Let's run the actual numbers from the paper. If you have a tiny circuit with just 5 modules, the algorithm checks 20 vertices. It completes in less than 1 millisecond.
Yeah.
Easy.
Yeah.
If you bump it to 10 modules, it checks 924 states. It still takes under a millisecond.
But now watch the curve. At 20 modules, you are suddenly checking over 350,000 states. It takes about half a second.
Wow.
And at just 30 modules, it balloons to roughly 601 million states. That takes about 19 seconds of pure processing time.
19 seconds for just 30 modules.
Yeah.
Modern chips have billions of modules. So how is this anything more than a fun, math experiment?
This is exactly where pragmatic engineering steps in to rescue the pure math. The author, Lux036, recognized that the design sweet spot, the pragmatic limit for exhaustive search, is exactly 10 modules. Beyond 10, you waste way too much time.
Okay.
So they utilized a strategy called multi-level integration.
Oh, this is a brilliant concept. Think of it like zooming out on Google Maps, right? You don't try to divide the entire country by looking at every individual house. First, you cluster the houses into neighborhoods. Then you cluster the neighborhoods into cities. Cities into states.
Exactly. In ADO, we call this contraction. The software takes the massive hypergraph of millions of modules and artificially merges them together.
Merges them.
Logic gates become larger blocks, blocks become subsystems. It contracts the graph repeatedly until it reaches what we call the leaf level. And they enforce a strict rule here that leaf level must be contracted down to exactly 10 supermodules or fewer.
And once we hit that 10 module limit size, the middle level's gray code tags in. It takes those 10 modules and exhaustively runs through all 924 possible states in less than a millisecond.
Yes.
It finds the mathematically perfect, globally optimal split for that contracted graph without getting bogged down in those exponential processing times.
And then once it anchors that perfect foundation at the bottom, it reverses the process. It projects the solution back up, unmerging the modules level by level. As the graph expands back into millions of modules, it uses our old friend, the FM algorithm, to do the localized fine-tuning refinement.
It's like the ultimate tag team. Gray code provides an unshakable, perfect anchor, and FM handles the massive scale refinement where gray code would just completely choke.
The experimental results from the paper bear this out perfectly, too. The author tested this hybrid approach on standard industry benchmarks, like the P1 benchmark, which consists of over 800 modules.
Right.
They ran a test comparing a limit size of 10 modules against a limit size of 20 modules.
Now wait, if it checks 20 modules exhaustively, that's 350,000 states. Shouldn't that give a much better result than checking just 10 modules?
You would definitely assume so, but both tests yielded an identical quality of results. Both achieved a cut cost of exactly 58.
Oh, wow. And surprisingly, both took roughly the same amount of time, around 22 to 24 milliseconds, because the FN refinement taking place at the higher levels consumes the bulk of the runtime anyway.
So checking more modules exhaustively doesn't actually help at all.
No, and that proves something crucial. The quality of the initial contraction phase really dominates the broader picture. Limiting the exhaustive search to 10 modules gives you a mathematically certified perfect anchor exactly where it exerts the most leverage without wasting any processing power on exponentially larger leaf levels.
So what does this all mean? We have a beautiful 2018 mathematical proof and this really clever multi-level map strategy. But taking pure theory from a math journal and making it run inside a production level C++ environment in 2026 is rarely a clean translation.
Oh, it was a massive engineering hurdle. The original code provided by Muetzi and Neumann Paulo was written under a GPL v2 license, and it relied heavily on C99 variable length arrays, or VLAs. Oh boy. Yeah, I know enough about modern C++ compilers to know why that's a complete nightmare. VLAs determine their memory size at runtime, right? But the industry standard compiler, MSVC, Microsoft's Visual C++ Fin, absolutely hates that. It demands to know stack sizes at compile time.
Yes. VLAs are fundamentally incompatible with MSVC, so the author had to painstakingly rip out all the variable length arrays and adapt the code to use std.vector on the heap, managing the memory allocations manually just to appease the compiler.
And the adaptation didn't stop at memory arrays either. The original math code used standard C function pointer callbacks, which is totally fine if you are just spitting out bit strings to prove a theorem.
Right.
But in a partitioning manager, you actually need to retain your state.
Right. A standard function pointer is basically amnesiac. It executes its function but completely forgets the context. So the author adapted the code to use modern std.function objects, specifically utilizing lambda captures.
I love how lambda captures work. It's like our hiker in the fog, right?
Right.
Instead of dropping their map and compass at every single checkpoint and trying to memorize the route, a lambda capture allows the algorithm to pack the entire netlist map and its current position into a backpack, dragging the whole state along with it as it traverses the middle levels graph.
Exactly. And they also had to fight the compiler on basic data movement. The author noted that MSVC tried to be overly helpful when the algorithm needed to copy arrays of integers that overlapped by a single index.
Uh-oh.
Yeah, MSVC defaulted to using a block mencpy, which completely corrupted the data because the source and destination were occupying the same space.
Oh, man. So the author actually had to go in and write manual right shift and left shift loops, moving the data bit by bit just to bypass the compiler's supposed optimizations.
Yeah.
You can have a brilliant Nobel-worthy math theorem, but you still end up in the trenches fighting a compiler over memory overlaps.
That is just the gritty reality of production code. They also had to optimize the cost tracking. When you are visiting 924 states in a single millisecond, you cannot afford to recalculate the entire cut cost of the microchip from scratch every single time you flip a bit.
Because that would mean counting millions of nets thousands of times a second. So how did they bypass that?
They made it strictly incremental. The cost tracking during the traversal is kept to big O of the degree. In simple terms, when you move one module, the algorithm only looks at the specific wires directly connected to that single module. It ignores the rest of the chip entirely.
That makes total sense.
It calculates the localized change, updates a running total, and moves on. Furthermore, the algorithm takes a snapshot of best part variable and tracks it throughout the entire cycle.
And it initializes that snapshot using the user's starting cost. That is such a brilliant failsafe. It guarantees that after the exhaustive search is complete, it will never, ever return a result worse than the initial guess you started with.
Exactly. The rigorous engineering really paid off. The adapted code passes all the complex test suites N5, N8, N11, Dwarf, ML, Mid, LVL. There are 0 regressions on the standard FM tests.
Amazing.
It compiles cleanly on both MSVC and G++day, though G++ still executes the tight loops about 20% faster. But the bottom line is that the code is robust and fully production ready.
It really is an incredible journey from a chalkboard to a microchip. We started with a fundamental bottleneck in chip design, right?
Yeah.
The FM algorithm getting stuck in local minima, unable to guarantee a perfect circuit split.
Then we pulled a 40-year-old combinatorial mystery off the shelf, finding Hamiltonian cycles in middle levels graphs. We realized that its mechanism of flipping exactly one bit at a time perfectly mirrored the module moving mechanics of FM.
And by merging the two using a multi-level strategy, we created a system that contracts the massive complexity of a modern chip down to a manageable 10-module leaf level. At that foundational layer, the math just takes over. It exhaustively checks every single possibility, guarantees a global optimum, and then hands the reins back to FM to expand it back up.
It replaces a localized, greedy guess with absolute mathematical certainty, placing that certainty exactly where it has the most structural leverage.
I really want you to think about this the next time you use a piece of heavily optimized tech. Every single ounce of speed in your daily devices relies on these invisible optimizations acting perfectly behind the scenes. We demand our hardware to be flawless, but that flawlessness is born from these incredibly gritty, complex marriages of pure theory and hard-fought engineering.
This raises an important question, though. The author explicitly notes the limitations of this current study. It only handles exactly balanced two-way partitions.
Right.
But if a seemingly useless, purely theoretical math puzzle from 1982 could unlock the perfect foundational split for modern circuit design in 2026, what else is out there?
Yeah.
What other purely abstract mathematical oddities are just sitting untouched in a university textbook right now, just waiting for the right engineer to translate them into code and solve tomorrow's biggest software bottlenecks?
It makes you wonder how many deep, sprawling canyons our hikers are missing right now, just waiting for someone to finally build a better map.